Hi, I'm Sebastian Thiele from the University of Paderborn. Today I present to you our tool that belongs to our tool paper, a tool suite for the model-driven software engineering of cyber-physical systems. The name of our tool is MechatronicUML Tool Suite. MechatronicUML enables you to model the software of mechatronic systems and provides editors for modeling the structure of the system, the behavior of its components, and the communication between the components. Our tool is especially designed for the MechatronicUML method, which defines a visual modeling language and a modeling process. Our tool also offers model-to-model transformations to various analysis tools. You can transform our models to UPAL models, which enables you a model checking of your discrete behavior. Furthermore, you can transform our models to the simulation tools MATLAB Simulink and Daimler. In this way, you can simulate not only the discrete behavior, but also the holistic system and see how it reacts to certain test cases. I will present the functionality of our MechatronicUML tool suite by following the modeling steps of our development process of mechatronic systems. In the first part of this video, we will use our MechatronicUML tool suite. For the simulation of the holistic system, we will use Daimler. For the demonstration of our tool, I'll take our running example. So consider the following situation. Two autonomous, driverless cars are driving in a line. Now the red car wants to overtake the yellow one. Therefore, they exchange messages in order to coordinate the overtaking. For example, the yellow may not accelerate during the overtaking. In the first step of the development process, you have to determine the structure of the system. So let's have a look at the component diagram of our system. So here's the component diagram of our example model. The system consists of 4 components. There are 2 software components, yellow software and red software. Their behavior will be specified within our process. And 2 continuous components, car and distance sensor, which we consider in our tool as black boxes, and their behavior has to be specified by other disciplines, such as control engineering. Our system is an instantiation of these components. Here you see a component instance configuration of our overtaking example. As you can see, we instantiated all components and connected their ports. The car component was instantiated twice. Over this assembly, both cars exchange their messages for the overtaking. In order to ensure a specific message-based coordination between these discrete components, we define the communication behavior between them with coordination protocols. In this case, we called our protocol overtaking. So let's see how such a protocol looks like. A protocol defines a detailed contract between 2 communication partners, called roles. In this case we have the role overtaker and overtakee. Each role represents a discrete port of a component. In particular, a protocol defines which role has to send which methods at which point in time, and at which points in time the role expects to receive a certain message. You can define the role message buffers and the messages that are received and sent by the role, and also the behavior is defined with the real-time state chart. So let's now have a look at the real-time state chart and therefore the behavior of the overtaker. So starting in the state init, we send a request to the overtakee, and wait for an answer of the overtake key. If we receive an accept message, we will go to the overtaking state and start overtaking the other car. If we receive a decline message, we go back to init and do nothing. The behavior of the overtake key role is described in another state chart, which I don't show here. After defining the role behavior, we can now verify it with UPAL. So we open again the protocol and here we can specify the verification properties. For example, AG not deadlock means that there may not be a situation where a deadlock occurs. I can now add new verification properties. For example, AG not buffer overflow, which checks whether a buffer overflow can occur. Now we start the model checking with UPAL. In the background, we transform our protocol into UPAL timed automata. We let UPAL verify all our properties and back translate the results. As we see, in our example, all properties are fulfilled. After designing the protocols, we can start to define the discrete component behavior. As you can see, the behavior is similar to the role overtaker. However, we added some additional constraints. For example, at this transition, we added a guard distance smaller 0.1, which means that the transition can only fire if the distance between the cars is smaller than 0.1. The refinements must not invalidate our model checking results. Therefore, not all refinements are allowed. We can check whether we did a correct refinement by going to the component diagram, and on the part of the component we can now check whether the refinement was correct or not. And as you can see, our refinements were correct. As soon as the discrete behavior is completely specified, we can go on with the holistic simulation within Daimler. So first we have to generate the Modelica code. In the folder source scan you can find the generated code. Now we can have a look at the generated model with Daimler. As you can see, our model was correctly transferred to Modelica. We still have our 5 components. The behavior of the 2 software components, red software and yellow software, was already defined within our tool, and I had to add the behavior of the continuous components yellow car, red car and the distance sensor. Now we are able to simulate the holistic system. And we can analyze the plot. So what I plotted here is the velocity of the yellow car in blue, the velocity of the red car in red, and the distance between the cars in green, and the purple line denotes the moment when the message for the overtaking is sent. So what happens here is that the red car is coming closer to the yellow car, and at a certain moment here the red car sends a request to the yellow car for the overtaking, and this request is accepted, and therefore the red car accelerates, it changes its velocity until it has overtaken the yellow car. Then it slows down again. And as you can see is that the distance between the cars is increasing again. This was the presentation of our tool. Thank you for your attention. We also want to thank all our students that helped us to develop the Fujaba Real-Time Tool Suite.